So I propose that we start. I'm going to introduce you officially. So it is a pleasure to have today Augusto Gerolin. That's how you pronounce it, right? Gerolin. He is a Canada Research Chair in Artificial Intelligence and the Interface of Chemistry and Mathematics. And he's an assistant professor at the University of Ottawa in two departments. I believe it's Mathematics and Statistics and the Chemistry and Biomolecular Sciences. Are those just two departments, or there are like 5 departments? Sounds to me like, but
no, there are two. There are two.
Previously, he was a Marie Curie Fellow at the University of Amsterdam in the Netherlands, and he obtained his PhD at the University of Pisa. Augusto's interests are in optimal transport, mathematical physics, and theoretical computational chemistry, and some mathematical aspects of machine learning theory, and he's going to be speaking about some of those things today. So a virtual applause for Augusto, and I'll leave you to it.
Federico, thank you very much for this very, very nice introduction. So, and also like to both Federico and Mircea for like inviting me to give a talk. So I have never been in Chile, so I have the impression that like I'm somehow in Chile at the moment. So this is my first experience talking to an audience that is in Chile. So I'm very happy that like you all decided to spend your lunch with me. So like my hope is that this is gonna be a little bit entertaining, or at least I hope. And I'm very happy if you ask questions and I have the chance to go a little bit more deep and talk more about the technical aspects of it. So like, if you see the title, I'm talking about Schrödinger Bridges, that I explain in a second what it is. But in particular, like, is the Synchron algorithm through the lens of optimal transport theory. And this, I want to make a disclaimer. Why I'm talking like about this through the lens of OT? Because like, just to check, do you see the new slide? Now I just moved the slide. It's working perfectly. So like a Synchron like is an algorithm that enters in a big umbrella, what is called like matrix scaling algorithms. And the basic question is very simple. So like given a non-negative matrix, can you find a diagonal matrix D1 and D2 such that the product of D1 times A times D2 is double stochastic? So you can think that like the projections are like the identity. So this is a very basic question. So like you have a matrix, you do very simple operations on the columns and the rows, and you can scale this matrix to the identity. So that is the goal. This is a very fundamental problem, and like the weak version of this problem was solved by Synchron in 1964. And like there will be like a lot of development and a lot of abstraction on this type of ideas, like in many different fields. And like if you are interested like to know this more deeply and to have like a wider view of like matrix scaling and Synchron algorithms, I really recommend you to look to this Martin Indel survey, where he explained like all the different sources of like Synchron algorithms and matrix scalers that appear in the market, like coming from potential optimization, like fixed point approach, convex optimization. So like what I'm gonna talk here today is very, very modest. And I'm basically on the intersection of like the yellow area, like entropy, iterative I projections, and convex optimization. So it's really, really like a tiny area, a tiny circle, but at least we can understand a lot of stuff on this. So, but remember, it's just a little piece of like a very big puzzle. And like, this is basically the plan of the talk today. So I'm gonna give a very overview of optimal transport before arriving to the entropic regularization of optimal transport and the Synchron algorithm. And then I will select like what I go a little bit deeper, depending on the questions, depends when you interrupt me, to speak a little bit more about the duality approach or go directly to a new variational proof. So a new variational proof of convergence of the Synchron algorithm. So that's a little bit the plan, but as you see, it's very flexible. I'm very happy to change it, and I have much more material that I'm supposed to have for a talk of this length. So let me start with some notation just to fix the notation, to introduce like some ideas. So like the problem that I'm interested to compute is like the Monge-Kantorovich formulation of optimal transport. So what is my data? My data are like two probability distributions that you can think about two discrete probabilities, like two histograms. Or you can also think about like two distributions in RD or in the real line, like those green bumps that I'm showing here. And I have a cost function C that here will be the distance or the distance square. The cost function can be quite general, but let's fix with the distance square. And what I want is to find the best coupling gamma. What is a coupling? So the coupling is a probability measure on the product space, RD times RD. So you can think about an example of a coupling, those red bumps that I'm showing here, such that the projections or the marginals are equal to the given distributions mu and u in RD. So, and I want to find the best. What the best means, like, is a coupling such that minimize like the total cost that is given by the integral of the distance square with respect to the gamma. So more precisely, so a coupling is a probability in the product space such that the projections are given by the given mu and u. So E1 and E2 are like the canonical projections in the first and the second space. If you prefer to think in the discrete setting, if you don't like a lot of measure theory, so like you can really think that like mu and nu are probability vectors. Your cost function is basically a matrix. Then this integral becomes just like a double sum of Cij, gamma ij, because also gamma ij become a matrix. And gamma ij is basically a matrix such that if you sum one of the variables, so is a ij, if you sum in j, this gives you mu I, sorry for the typo, this gives mu I for every I. And if you sum in I, this gives you yj, mu j for every j. So that up, so you choose if you want to think like in a more abstract level, has measures, probability distributions, or like discrete distributions. And like, and what is very fun about this problem that you can do very cool things. So for example, imagine that mu and u are like the color palette of a Picasso painting and a color palette of La Gioconda. So you can really think that like the colors of Picasso, the colors of La Gioconda like has two histograms. So where like every point is a point in R3, and each component are like colors of red, green, and blue. So RGB. And so like mu and u are two histograms. And like by solving this problem, something very nice that you can do is that you can send the colors of Picasso to La Gioconda and colors of La Gioconda to Picasso. And the reason why is that like this variational problem defines a very natural distance in the space of probability measures or in the space of probability distribution that is the so-called like two Wasserstein distance. Like, and in a sort of distance that like are very powerful and respect like the geometry of the data. So it's not an Euclidean space, but like is a kind of geometry that are very natural when you are dealing with histograms or probability distributions. So I'm gonna show some examples. So as I said before, like this defines the space, a distance in the space of probability measures. So like P2 are like the space of probability measures with finite second moments. And Wasserstein 2 is the distance defined by this variational problem. And this is a very robust distance because it allows you to compare not only two data that are discrete or two data that are continuous, but also data that are one discrete and one continuous. And one fundamental theorem in optimal transport theory says that like the minimizing gamma, the coupling gamma that minimizes this problem is extremely sparse. It's actually concentrating the graph of a map, like I'm showing this picture. So like this gamma, although a priori we are taking like all types of objects that lives on RD times RD, they are actually a very low dimensional object. So if you think in terms of a matrix, the optimal gamma is a very sparse matrix. So it's zero almost everywhere, but on the graph of a function. And so therefore, like you can compute this Wasserstein distance by just solving an integral in RD. And this will be like the cost, so x minus t, where t is the graph of this, where gamma is concentrated. This is very well known, like by the Brenier theorem, and you say that t is the Brenier map. And why this is very interesting, because like this distance metrizes the weak star convergence or the convergence law, the convergence probability. So like this is a very weak metric dealing with distributions, dealing with or discrete probability objects. So, and like more an intuition, just to grasp a little bit why this is very interesting. So like, if you want to take a very concrete example, like take two probability distributions in R. So the Wasserstein distance is a sort of like a horizontal distance between the two probability distributions. So what I mean by horizontal distance, so imagine that you are comparing two distributions, F and G. So F and G are basically the densities of mu and u, are the probability densities of mu and u. If you compare F and G, use for example the L2 distance or any LP distance, they are basically telling you like the difference on the vertical difference between F and G. While like the Wasserstein distance is telling you how is the horizontal displacement between those two distributions. So like the distance between F and G are basically the distance between X and T of X. So and this like is so let's take an extreme case to get an example. Imagine that F is a bump. So like, I don't know, some Gaussian in a compact set, and G is basically a translation of this Gaussian that has joint support. So if you compare the LP distance between those two guys, they are going to tell you like that in LP distance, those two bumps are very far apart of each other because they have disjoint support. While in the Wasserstein distance, they are going to tell you like that those bumps are distant for each other due to their horizontal distance. So like the modulus of their horizontal distance. So geometrically, it makes a lot of sense to think about this kind of distance. So a second example, like imagine that you are doing like a L2 interpolation. So like the purple is the first distribution, the yellow is a second distribution. So when you have a distance, you can talk about geodesics and you can talk about interpolations. So if you do a simple convex interpolation between two distributions using the L2 distance, you have like this creation and destruction of mass on your distribution. While if you talk about like Wasserstein geodesics, you have like a kind of curve or a kind of interpolation that like respect the geometry of the data. That is very natural interpolation between the purple, the first distribution, to the yellow, the second one. So this kind of ideas has been using, for example, in computer vision. So you can really like make an evolution of like histograms between two pictures. So for example, the picture on the bottom left to the picture to the top right. So you can see really how is the evolution of like the histograms of the color palette of those pictures. And you see like that is a very natural in the eyes metric, the kind of colors that you get, the kind of interpolation that you get. And this idea has been used also by people at the Pixar to make like movies on some of their cartoons when they are doing movies. So like in their case, the problem that they are studying is a little bit more abstract than the one that I presented here. So instead of having like two given probability distributions, they have three. You could have like finitely many. So and those three distributions are basically like the uniform distributions on those shapes. So you can think that like the characteristic function of the donut, the characteristic function of the pig, and the characteristic function of the duck are like probability distributions. You just need that they integrates to one. And by using like this kind of technology, by analyzing like the geodesics and the interpolations along those Wasserstein or optimal transport geodesics, like you have a very natural way of like moving one shape to the other. And this like this is a very nice paper with like a lot of nice images, and I really like particularly this one. So another aspect that becomes very popular, the use of optimal transport or like the vastest time distance, was like in generative models. But like what I'm gonna tell here, like applies to any type of machine learning problem that you are interested in. So like the main idea in the context of like the generative adversarial networks, I'm not gonna enter in the detail, but like the main idea, like it was to change the kind of metric, so the kind of loss function that it was used, instead of using like the Kullback-Leibler divergence or like the Jensen-Shannon, because they were looking to something that is symmetric, they say, why not to replace like those kind of like standard divergence or like standard distance that we use as a loss function, why not to plug it an optimal transport distance? Like, and basically the insight that it was given is very close to the insight that I gave about the bumps between the two Gaussians. So the insight that they present in the paper, they say, oh, it's very natural to use the vastest time distance, and we have some gain numerically for the following reason. The gain from the stability viewpoint. So for the following reason, imagine that you have like those two distributions. So one that is like the uniform distributions on the line that are centered on x equals to 1. And the other one, like, are a family of distributions that are also uniform, but centered when x is equal to theta. So those are those two lines. So if you compute the Kullback-Leibler divergence between those two guys, since you need to do like log p0 divided by p theta, so what you have is basically 0 if like those two distributions overlap, if theta is equal to 1, sorry, not if theta is equals to 0, but theta equals to 1, when they overlap is 0, or plus infinite otherwise, because they have disjoint support. And it's the same thing if you do the symmetrizing version, if you do the Jensen-Shannon divergence. So it's 0 when theta is equals to 1, when they overlap, and it's log 2, so it's not infinite anymore, but it's the same value regardless of the distance, regardless of if theta is far apart or very close to 1. But if you do the computation with the vastest time distance, what we are going to get is that if the two vastest time distance between those two guys are basically like the modulus square of theta. So tells you really the horizontal distance between those two probability distributions. And like the main argument in those papers in generative adversarial networks that like due to this singularity that you get when distributions has disjoint support, by using optimal transport distance, you are gonna get more, you're gonna improve the robustness of the algorithm. So you would not fall down in those kind of critical points or those singularities. So, okay, I say a little bit about like different ways of comparing distribution. So optimal transport has been used in different kind of context. But the question that you should be asking now is like how to compute it, how to solve it numerically. So in this pass through the Synchron algorithm and then entropic regularization, at least the method of choice of solving this kind of problems has been to use like the entropic regularization. So what I'm doing here, I'm changing a little bit the notation. So now my data are mu1 and mu2. And I have, like before, the same kind of function, also integral of my cost function with respect to the gamma. But now I'm adding an entropic term. So I have an epsilon, that is my regularization parameter, that is like a non-negative number. And I'm adding an entropy. So that is gamma log gamma. Since I don't have a reference measure, since it's not clear to me what would be like a natural reference where I do the integration, I'm taking my data, rho 1 and rho 2, and I'm integrating with respect to the rho 1 times the rho 2. So to be very precise, so gamma is the density I'm identifying the density and the measure gamma with respect to the reference measure rho 1 times rho 2. If you prefer, you could also do the same thing integrating with Lebesgue. X and Y are subsets of RD. So you could also do the same thing integrating dx dy. So, and what is nice about this problem? The nice aspect about this problem is that like this makes this functional in function of gamma, what I'm minimizing, a strictly convex functional. And I can show that there is a unique minimizer, gamma, that is given by A times B times exponential of minus c divided by epsilon. So you have like this sort of Gibbs energy that is the minimizer of this problem. So it's very nice. It's very nice a way of thinking about it. So like if you compute the first variation of this problem, you can basically see that what you get is exponential of minus c divided by epsilon. And you can really think that like A and B are the Lagrange multipliers that prevents that your optimal gamma epsilon has the correct marginals ρ1 and ρ2. So saying in another way, so there is a very nice way of massage is functional, and you can write it like the epsilon, the integral of gamma log gamma divided by exponential of minus c divided by epsilon. So looking to the functional on the top, so you know that the Kullback-Leibler, so the entropy in the way that I'm writing here, is always non-negative. So you know that you are minimizing it when the entropy is 0. So you know that you are minimizing it when gamma is equal to exponential of minus c divided by epsilon. So then like your minimum would be exponential of minus c divided by epsilon, but you should remember that like you are not minimizing among all gammas, but you are minimizing among the gammas that has the correct marginals ρ1 and ρ2. So then in the end of the day, your minimum is not like exponential of minus c divided by epsilon, but like you need to multiply two functions n and b that are like sort of weights that prevents that your gamma has the correct marginals ρ1 and ρ2. I don't know if it's very clear, but it's just an intuition. I'm just trying to give an intuition why it works, shaking the hands. So, and what the entropy does is basically add some noise, add some stochasticity. Oh, yes, Ricardo, please. Very nice that you are here.
Yes, thank you very much, Professor. I have a simple question. A and B
Yes.
are elevated to epsilon or is a parameter? I
No,
mean
A
that
and B.
A and B are elevated to epsilon. I mean, when epsilon is 0, this A and B converts to 1.
Is not the power. So
No, it's not
A
the power.
and B are basically that I'm telling you that this is a little bit tricky, that those A and B depends on epsilon. So if I choose
Perfect.
epsilon 1, I have one A and B. If epsilon is 100, I have difference A and B.
Perfect, perfect,
So this is not only a function of X and Y, but is also a function of epsilon.
perfect. Thank you very much.
Thank you for the question. Please, guys, interrupt more because like this is very important also to me to guide if I go to left or right. Thank you very much for the question, Ricardo. I'm super happy that you are here. So the idea the idea of the regularization parameter or the idea of adding the entropy is that like you go from a regime when like you have like geodesics between mu and nu. So mu is the red distribution, the dots, you have a discrete distribution. Nu is the blue distribution represented by blue. So you go to this direction that you have a map linking the first distribution to other distributions that like you have some noise that scales like with this square root of epsilon. So like instead of having like geodesics, you can think that you have like a Brownian bridge between like those two distributions. And like you have a Brownian motion like linking one point to the other. So you add some noise and you add some stochasticity. From like the picture that I showed you before, so like when epsilon increases, you leave a regime where like your matrix gamma, the optimal gamma when epsilon equals to 0 is very sparse, to a regime where you have like a sort of anarchy. So when epsilon is very big and you go to infinity, you lose this sparsity and you are really in a situation where the independent measure dominates. So like that your optimal gamma is really ρ1 times ρ2. That is what I'm representing in the picture on the right. So like you go to this regime where like your data X and Y is completely determined by a map. So see on the left side, like given X, you have only one option of Y until the last picture that like for every X, all the Ys are possible. Mircea, open your heart.
Yeah, thank you. Okay. So I wanted to ask when you show these Brownian paths, or you talk about noise, is it? Do you know if because if on the left here there is this Benamou-Brenier version of optimal transport where things are moving along paths with a continuity equation, and they go from the first measure to the second, and you have these paths. But when I have epsilon non-zero, then do you have some kind of Brownian paths, Benamou-Brenier, Is there really a Brownian path in a model like Benamou-Brenier of this? Yeah. So, who is formulating that? How do? Yeah.
Okay, that is a very good question. So
I mean, what is the Brownian?
Okay, from the PDE viewpoint is easier. So like, if you want to think this on the PDE level, so when epsilon goes to 0, you are like minimizing the kinetic energy, so the velocity field in the Wasserstein sense, along the continuity equation. So in the constraint, you have like the continuity equation that is basically telling you that you are preserving mass. When you go to epsilon equals to 1, or with epsilon positive, you just need to replace the continuity equation to the Fokker-Planck equation. So you have the continuity equation equal epsilon divided by 2, or a scale that I don't remember, and you have like the Laplacian. So you add some, that is how you could think the noise. So instead of moving along the continuity equation, you are moving along the Fokker-Planck equation. And this is precisely the Brownian motion in the PD level.
I mean, the Laplacian is like you have the distribution of the Brownian motion that is going with the Laplacian.
Exactly. Your rho t is moving with the Fokker-Planck equation. So you have like the continuity equation plus a noise term. So it's really a Brownian motion. It's really a Brownian bridge.
I mean, yeah. Because I mean, for example, in these books, then you have a measure over paths that are continuum paths, and then you have all this functional analysis on the space of paths, of continuous paths, and then you have solutions of the continuity equation. But is there? So then you can define a measure that is the measure on Brownian paths, right? The Brownian measure on paths.
Okay, no.
You can also do that, right?
Yeah, but I think that you are thinking more abstract than what I was saying. What I'm saying that like you have rho t that is measuring P2 RD. So I'm not on the PET space. And has a measuring P2 RD, this solves the Fokker-Planck equation. So that's what I'm saying. So you can translate, the Schrödinger problem is posed on PET space, but here I'm talking about a simplified version. So in this, you are correct.
Okay, I see.
Thank you for the question. This is very, very nice. So like you go from so the solution of gamma when epsilon increases, you go from a sparse level to a less sparse matrix. Of course, like this is something that you can play around numerically, and this is what I'm gonna say in the following. So like, and if you wanted to compute this optimal gamma, so like what we should do, so we should use the following theorem. Gamma is a minimizer having this shape because it's unique and has this shape, if and only if it solves the so-called Schrödinger system, which appears for the first time in a paper of Schrödinger in 32. So, and what is the Schrödinger system? The Schrödinger system is something super simple. Like what I'm doing this Schrödinger system is the following. I know that the minimizer is unique and has this shape, a times b exponential of minus c divided by epsilon. And I also know that by definition, like the minimizer should have the correct marginals rho 1 and rho 2. So then what I do, I take gamma epsilon and I integrate with respect to rho 2. When I integrate with respect to rho 2, this should be equals to 1. Because I know that gamma has the correct marginals rho 1 and rho 2. And since I'm integrating with rho 2 that depends on y, I put the function a that depends on x outside. And the same, I integrate with respect to rho 1, I get the second equation. and since rho 1 depends on x, I put the epsilon outside. So if I want to decide who is epsilon, I need basically to discover who is A and B that solve the system. So I know very few examples of ways of solving this system analytically. So, or maybe an example of solving the system analytically is when like my cost function is the distance square, and rho 1 and rho 2 are like Gaussians of any dimension. And the reason why I know how to do this when I have multi-dimensional Gaussians is because like when C is the distance square, A and B will be morally exponential of quadratic functions. So if you are in the real line, A and B will be exponentials of polynomials of degree 2, of at most degree 2. Then like when I impose this condition, my guess is that A and B will be exponential of polynomials of degree 2. Then I can just plug it in the equation and find the best coefficients of A and B. Since I know that this is the unique and has this shape, then I won. And why I have this intuition that is the exponential of a polynomial of degree 2? Because I say, if my marginals are Gaussian, the only thing that can happen is that like the gamma will be also a Gaussian in the space RD times RD. So that is the sort of intuition. So in this like is a very natural approach. It was not the only way of getting it. It was studied by different people in statistics and machine learning. I also did this very stupid computation with some co-authors, but it's a very nice result because it gives you an analytic solution. And otherwise, you don't know how to solve this analytically, and you can compute with the Synchron algorithm. And how does it work? So the Synchron algorithm, yes, Ricardo, please.
Just to know, I know that this is not so central to this, but A and B, when row 1 and 2 are Gaussian, and these A and B are exponential of polynomial of degree 2, these A and B are log concave functions or log convex functions?
Depending on like, no, I don't know if you can say something like this, but like we may be able to say something if we assume something on the marginals. So like rho 1 and rho 2, so that is the game. If you want to think this very abstractly or get a feeling, like A and B are dual variables of rho 1 and rho 2. Perfect. And richer are your rho 1 and rho 2, more complex are going to be A and B. So since like Gaussians, you can completely represent with their mean, completely characterize with their mean and their covariance matrices, then A and B are very simple. So if you start having like mixed Gaussians, then A and B are going to be more complicated. So like that is the game to play. If you make hypothesis of rho 1 and rho 2, you can say something about A and B, or at least theoretically, but that is the kind of game. And that's why compute it numerically can be very tough.
Perfect. Thank you very much, Professor.
No, thank you for the question. So this is very nice. So like compute numerically, the algorithm is very simple, but like the performance of the algorithm can vary a lot depending on the complexity of rho 1 and rho 2. So that's what I want to say.
So if what you said there, does that show like maybe a more general strategy of when you can find analytic solutions? Like, of course, a Gaussian only, you can determine it with 2 parameters only, but if there was a distribution like with only 4 moments, would you be able to do the same trick and maybe get something out of there? Some analytic?
Theoretically, yes. I'm not aware of like people who have done a computation like this. We didn't do, but theoretically is you can like define a class of rho 1 and rho 2 that in theory you could solve because you can guess what are like the classes of A and B. That is so the nice stuff of the Gaussian, like that, this gives you like a benchmark. That's why people like it. So that you can really like do in any dimension. So since it's analytical, you can solve in dimension 1000 or 10,000. That's why people like it. But it's a very simple idea. So it's really, so and how to do this in general? Thank you very much for the question. So how to compute it with using the Synchron algorithm? This is like the simplest algorithm that you may know. So what we do is we use the Schrödinger system. You know that we need to find A and B. So what we do, we start A and B with the identity because we don't know what is A and B is. We just initialize it. And then we take the first or the second equation and you divide the integral and pass to the other side. Then you can compute Bn using the A0 that we initialize. When we compute the A0, we use the second equation, and then I divide and I use the B1 that I compute in the previous iteration. And then I keep doing it. So I have B1, I have A1, then I use A1 in the first equation to compute B2. When I have B2, I can compute A2 as well. And you keep doing this. And like this is very fundamental algorithm that this has been studied by different people in different contexts. When rho 1 and rho 2 is discrete, when rho 2 and rho 1 is continuous, the kind of techniques that you use to prove a convergence and theoretical guarantees for this kind of problem changes. And like just to give a little idea on how this is in general proved in the works of Franklin Lawrence and also like some ideas in the Synchron, the way that people proved this previously, they consider like the cone of two sets. So if you take like, for example, the matrix or like the probabilities gamma such that just one of the marginals are correct and the second one is not necessarily rho 2, and you take the other set of probabilities gamma such that only the rho 2 is correct but not necessarily the rho 1, this guy form a cone. In this cone you can put like the so-called Hilbert metric that like intuitively speaking is the angle. The Hilbert metric gives you the angle on this cone. And basically what people show that like when you do the Synchron iterations, you are like missing up one of the marginals, but you are computing precisely the second one. And when you do again, you mess up a little bit the one that you compute well, but the other is a little bit better than before. And you keep doing this. In a very abstract term, so what they are telling you is that like the Synchron iterations is a contraction on this Hilbert metric. So since this is a contraction, there is a fixed point. So by the fixed point argument, you get the convergence. And you not only get the convergence, but you also get the rate of convergence for free. So how fast you converge to the optimal solution. So I'm just giving you a taste. If you are more interested on that, again, Martin Indel is the best survey ever to understand like all the numerical viewpoint and the connections between the different people who study this algorithm. But also like there are two very nice surveys by Christian Leonard, Chen, Georgiou, and Pavon that look to this problem more from a probabilistic viewpoint on large deviations and stochastic control, which is like very complementary to the survey of Indel. Okay. So then I tell you a little bit like just to try to say 5-10 minutes to not go too much over time. So what was like my business on this kind of Synchron algorithm? So the reason why I get interested about the Synchron algorithm is because like I was interested in the problem of Pixar that I showed before, where like instead of having two marginals, we can have like finitely many, 3 marginals. And like the kind of strategy of this like contraction argument is not very natural when you have like 3 marginals. So when you have 3 marginals, instead of having like a system of 2 equations, you have a system of 3 equations or finitely many equations where you need to fix like all the any projections where any are the number of data that you have, rho 1, rho 2, rho n. And like this kind of fixed point argument, it's very hard to do a proof, or at least I was not able to do a proof, because you would have like a finite number of angles that you need to control, and you need to show that at the same time, all the angles are contracting. So I tried to do this computation, I was not able to. And like the way that I analyze this problem is using like a sort of dual formulation. Basically, what the strategy that we developed like basically show that like the problem that I showed previously, where you are minimizing the integral of the cost function with respect to the gamma plus an entropic term, this can be equivalent study by a supremum of what is so-called the dual functional or the Kantorovich formulation of optimal transport. That you are basically finding the maximum functions u and v, such that those functions maximize the integral of u with respect to the rho, integral of v with respect to the rho 2, minus an extra term that is exponential of the integral in the product space of exponential of u plus v minus c divided by epsilon. So like you could, instead of looking to the previous problem as a minimization problem, you could look at it as like a maximization problem. And basically with collaborators, I showed that like this maximizer exists. And like basically the A and B functions in the previous slide are basically exponential of u and exponential of v. So A is basically the exponential of u of x, and B is exponential of v of y, where u and v are functions that maximize this dual problem, maximize this variational problem, where I'm taking the sup of the dual functional over the functions u and v that are L1 functions that are continuous and bounded, like those Lx x space like are just like the minimal assumption that you should require such that the function of the epsilon is well defined. So like to say in very few words, so you could have a different viewpoint of the previous problem and look like as a maximization of potentials u and v instead of looking as a minimization of a coupling gamma. So to go a little bit to the substance, basically what you can show that are completely equivalent is that like u and v are maximizing potentials for the dual problem, and that basically u and v solves the Schrödinger system. So gamma that is optimal is given by exponential of u plus v minus c divided by epsilon. And if you plug u and v, the ones that maximize the dual problem, then the optimal gamma is given by this guy. So you are sure that this guy has the correct marginals. And in particular, that like the minimization problem has an energy. So the number that I get when I'm minimizing in gamma is the same number that I get when I'm maximizing u and v. So that is, roughly speaking, is the good idea. And with a collaborator, Simone Di Marino, we basically show that like you could have a different viewpoint of proving the convergence of the Synchron algorithm that is much more variational. And the theorem is the following. So like if we start with like AN and BN that are like the Synchron iterates that are also called sometimes iterative proportional fitting procedure, then like what you can basically show that like up to scaling of a scalar, you can show that like that Synchron iterates converges to a function A in LP, and the Bn, the Synchron iterates given by Bn, converts to a function B in LP, such that A and B solve the Schrödinger system. So in particular, if I define a gamma n that is basically An times Bn times exponential of minus c epsilon, I can show that this gamma n converges in LP for any p to gamma epsilon. That is the optimal solution of the Schrödinger system. Because I know that like A and B are unique when I'm able to solve the Schrödinger system. And the basic idea to prove this theorem using our strategy is basically do a very simple change of coordinate on the Synchron iterates. So what I do is I write An and Bn as exponential of my potentials Un and Vn. And instead of thinking that I'm like correcting the marginals A and B, I'm correcting my potentials A and B, the way that I'm gonna think about this is that I'm doing like a gradient ascent on the dual functional U. So basically like what the Synchron algorithm is doing is like an alternate maximization in the dual problem U, where like I first maximize U keeping V fixed, and then I maximize V keeping the U fixed. So it's a very variational problem. So basically the argument shows that like you get the Synchron sequence An and Bn. Thanks to a property of a transformer, I can get some compactness. And this compactness allow me to extract a subsequence that is monotonically increasing in the sense of the dual problem, and that there's have a convergent subsequence. And all the game is to show that like this convergent subsequence converges to U and B that solves the Schrödinger system when you take the exponential of U and exponential of V. This like a very proof shaking the hands. So like you can think about Synchron also has an alternate maximization in the dual problem. And what is very nice about this approach is that like this generalizes very well if you have more than 2 marginals, if you have 3, 4, or any marginals. And also like this also accommodate other types of regularizations that is not necessarily like the entropic regularization. So in the beginning, I could, for example, instead of adding the Shannon entropy, I should have added, I don't know, a power of gamma. I don't know, the square. Because I want to get some sparsity. I don't like that my coupling when epsilon is too big is like a very sparse, not sparse. And this approach generalizes also very well for different entropies. So I'm very sorry that I was very fast in this end, but I'm very happy that you ask a lot of questions. And I just want to give a little bit a taste of what like was my contribution. So I'm over here, so open to questions. Ricardo, please.
Thank you very much for the presentation, Professor. Was very. There is any chance that you can send this PowerPoint to an email, or this
Of
can
course.
be shared? This can be shared.
No problem. Like I didn't see share anything in this slide. So just send me an email. You know my email, and I just share with you.
And I have a second question. The D in the dual problem
Yes.
is strictly concave. Is strictly that D epsilon
Yes.
is strictly concave.
Exactly. So that's why it's very easy. So like to get the existence of the maximizer, this follows from the direct method of calculus of variations, because like it's concave, and you just need to get some compactness of the maximizing sequence.
Perfect. Very beautiful.
And you have like uniqueness up to translation. So you can see that like it's a little bit, this is a little bit annoying that like if you take U and V, you can also take U minus A and V plus A, where A is a constant, U plus constant, V minus constant. And you see that like the cost does not change when you add and subtract a constant. So it's a little bit annoying that you have this invariance by translation. This make like the computation to get the existence a little bit harder, but not too much harder.
Perfect.
But it's true, it's concave.
Thank you very much for that.
So I'm very happy. Yeah.
I'm gonna ask a question. Oh, and Anastasius is gonna ask a question. Anastasius first.
Let me unmute. All right, very nice talk. Thanks.
Thank you.
So just a quick question. I know that this was not the main focus, and I'm not an expert in this area, but how much is known about the asymptotics of the minima of the regularized function? So the regularized functionals are strictly convex, which is nice. Presumably some gamma convergence argument should be made there to say something about the asymptotics of the minimizers of the regular. So the original functional is not convex, right? You might have multiple minima. And the intuition, of course, is you regularize it as epsilon goes to 0, you're close to some of these multiple minima, presumably, right? But has any of that been established, or?
Yes, I'm putting some reference on the chat. So like what I'm saying, the easy computation that I did as well is like to say that like gamma converges to gamma when epsilon goes to 0. So like that, I'm not only saying that like when you take the minimum of an integral, just to give a context to everyone. So when you take a minimum of an integral, this is a number. So I'm not only saying that like those functionals are converge has energy, so the cost of the epsilon, converge has a number to the epsilon, but I'm also saying that like any minimized sequence, gamma epsilon, converges to the argmin of the problem when epsilon is equal to 0.
Yeah, that's
so
the gamma convergence, yeah.
Yeah, exactly. So then like this is known when epsilon goes to 0, but like you are right. The nice question to ask, like what happens in the next term, right? So what is the next time asymptotic? So I'm putting you, so what you can say is that like the gamma that you are converging is the one that has the minimal entropy. That is what you get with the second asymptotics. And there are very nice works. So like there is those like by Giovanni Conforti and Luca Tamanini that I put on the chat. And there is also a paper with like 1,000 of authors, and 2 of the authors are Lenaïque Chiza, and Flavien Léger. And there are some authors that they do also like a smart computation with the first order. And I like a lot another paper of like Jean Louet and Simone Di Marino that they study like in the 1D case. And what I like about the 1D case is that everything is almost explicit, so you can touch it. So this is like, maybe the last one is not like the most general result, but it's a very nice one to get some intuition what is going on.
It's more hands-on, but you have a nice characterization. So if I got that right, so basically your minima in the regularized functions converge. You have a very nice characterization of the gamma limit of the, so it's the maximum entropy, right? Is that what you said? The gamma limit of the minimum of the regularized functionals is the maximum entropy minimum of the original functional. That's
exactly.
Right.
What like I should also add that like if you take the solution when when epsilon is 0, this guy is a singular measure in the product space, right? This is concentrated on a map. So like this guy has maximal entropy is plus infinity.
I see.
So this is not very useful in practice because like if you don't have uniqueness, but like your 2 minimum are guys that are singular with respect to the product ρ1 times ρ2, you cannot distinguish. So you can distinguish when you have some guy that is singular and some guy that is fat, some height that has a density. But if both of them are singular, this characterization don't help you, so you need to go a next order. And it's horrible that we don't know a lot about the next order.
That's great. Thank you very much. Yeah.
I'm gonna ask you guys all a favor. I'm very happy to come again to ask to have a Zoom call with any of you that you have if you have questions. Also answer the email. It's just that like I invite someone for a seminar, and the seminar is starting in 1 minute, and I will be like the worst host ever if I don't show up in time because everyone is already in the room, and they are bombarding me with emails.
Yes. Thank you very much, Augusto. We loved the talk. Where all the people who want to ask questions should email Augusto, and virtual applause from me, and I'm sure from everyone else in the audience. So thank you for coming, and let's hope we keep in touch.
No, fantastic. Very happy to keep in touch. Thank you all for sharing your lunch with me.